Hi there. Let's dive into this very interesting topic of the stability of different cyclic compounds, right? So, the moment I say cyclic compounds, I'm sure one thing that strikes the doors of your mind is going to be benzene, which is the OG, the famous, the original benzene. And benzene looks like this. And the moment you see there are these pi bonds which are getting delocalized, and when you see this, we immediately call it aromatic, right? So benzene is the famous example of aromatic compound. But what exactly is aromaticity? So aromaticity is nothing but a cyclic conjugated unsaturated molecule. Now this word is important. Listen to it carefully. Conjugated. Remember, conjugations can be of different types, like a double bond conjugation. There can be double bond and a lone pair conjugation. There can be a double bond and an empty orbital conjugation. There can be a double bond and a plus charge conjugation, right? There can be a double bond and a minus charge, in fact, like this, conjugated to a double bond. So there can be different types of conjugation. So beware, it is not always that a double bond is going to be conjugated to a double bond. Right? So this we have done while talking about resonance. So cyclic conjugated unsaturated molecular ion that is stabilized by pi electron delocalization. Now this word itself speaks a lot. Our agenda is to find out the cyclic compounds, which kind of cyclic compounds are stable. And here the definition of aromaticity itself talks about the stability coming due to the pi electron delocalization. Now the moment I say a compound can be classified into a kind of three different categories, I'm sure three categories that should instantaneously strike the doors of your mind are aromatic, anti-aromatic and non-aromatic, right? Aromatic, knock knock, whom can we say are aromatic? Can you think about that? Yeah, the one that follows Huckel's rule. We have done this. So Huckel rule's condition, do you remember? First thing is, of course, since we're talking about the cyclic compounds, the compound has to be cyclic. That's there. But other than that, there has to be planarity, there has to be conjugation, and this is the most important. There has to be 4n plus 2 pi electrons, right? How you saw in benzene? So in benzene, how many electrons were there? 6 pi electrons. So I can write it like this: 4 into 1 plus 2 pi electrons. So 6 pi electrons. So this is henceforth aromatic, like we were saying it since now a long time. So n here can be any number. It can be any whole number. It can be 0, 1, 2, 3, can be any number, right? Including 0. But anti-aromatic compounds are kind of like the conditions. These three conditions are absolutely copy-paste. Control C, Control V. But do you see a point of difference? Do you see this? Here we have 4n pi electrons. So you can think of a cyclobutadiene like this. How many pi electrons? So there is cyclic, there is planarity, there is conjugation, and there are 4 pi electrons. So what is the n here? N here is 1. Mind you, this n here can be only natural number, not a whole number, meaning it cannot be 0 for anti-aromatic compounds, right? Now, there is a complimentary gift for you. If you have understood aromatic and anti-aromatic compound, non-aromatic compounds understanding comes as a gift for you. So this is a gift. Anything which is not aromatic and anti-aromatic will be non-aromatic. So what if something is not cyclic? So do you see cyclic and cyclic? Something is not cyclic, like this kind of a molecule. Not cyclic, what shall it be? Non-aromatic. Or let's say in the ring we have one of the carbons as sp3 hybridized. So hybridized, one of the carbons is sp3 hybridized, means there is non-planarity here. sp3 means tetrahedral. So of course there is non-planarity. Okay, even though it is cyclic. So that also becomes non-aromatic, right? So anything which is not aromatic or anti-aromatic can be classified as non-aromatic compounds. Now that you know the three classification and you have revised these three classifications, coming back to the stability. Coming back to the stability. Now these guys out here, the aromatic compounds, we are again and again saying they are very stable because of the pi electron delocalization. But we are not using any such term with anti-aromatic compound. Let's understand why are we so anti about them. No. There's nothing to be anti about anti-aromatic compound. It's just that the electrons enter the anti-bonding molecular orbitals. Remember from molecular orbital theory, anti-bonding molecular orbitals. So in chemical bonding, MOT, we have learned about the anti-bonding molecular orbital. So there's a little recap for you. If you remember, we were finding bond orders there, number of electrons in bonding orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2. So if more the electrons were entering the anti-bonding, the bond order was decreasing and the strength was decreasing. So here you can remember it as more the electrons that enter anti-bonding molecular orbitals, more will be the unstability. Now, if a compound has a chance, for example, look at this 8-membered ring. If a molecule has a chance of becoming non-planar in order to become stable, it will, even though it has 8 pi electrons, for example, or 4n pi electrons. So any such compound which has an option. So for example, when we took this buta-1,3-diene, the cyclobuta-1,3-diene example, if you remember when I was talking about this, it is a small ring. There is no option of going out of the plane. But with the 8-membered ring, there is an option of going out of the plane. So it doesn't exist like this. Rather, the 8-membered ring exists like a tub-like structure because if you count the electrons, yes, 1, 2, 3, 4, 5, 6, 7, 8 pi electrons. But if you look at the structure, it is tub-like structure. What does this indicate? That any anti-aromatic compound, if given a chance, would not want to become anti. Rather, it would want to become non-aromatic, right? That means going out of the plane. It is not planar anymore. So, by this, we can predict the stability as well. So, I'm sure it is clear now that aromatic guys are the most stable ones. Then comes the non-aromatic guys, and then comes the anti-aromatic ones. These anti ones are least stable, like I said, because the electrons are entering anti-bonding molecular orbitals, which is producing instability. So we can avoid that stability. Life and chemistry is all about stability. So here is a question waiting for you. Let's see if you can do it. What do you have to tell? The order of stabilities of the following compounds. First thing first. Are you able to decode what is this first compound? This looks like benzene, benzene and benzene. Well, this is the famous example of aromatic compounds, aromatic systems. This is phenolphthalein. So this is certainly when we have benzenes condensed together, we call it, that is also aromatic. So this is certainly aromatic. Okay, next one, do you see these carbons? These all are sp3 hybridized. That means there is non-planarity. So third one is non-aromatic. And hey, we have been doing second one now for a long time. So this is of course 4 pi electrons, you can check. Okay. So this is anti-aromatic. Now for aromatic, you need not to always keep counting the pi electrons. If you see there is a benzene, one single benzene is enough to make a molecule aromatic. Keep that in mind. Okay. So here we have at least 3 benzenes. So this is a benzenoid system, aromatic. So now out of 1, 2, and 3, most stable is of course the aromatic system, then the non-aromatic, that means the third one, and then the anti-aromatic. There you go.